Data are increasingly important in our world. Our efforts to teach statistical thinking are being guided by research on how people think about data. As part of the Data Games project, we're exploring a specific data handling skill that there has been almost no research about, and that is how people systematically record and organize data that consist of observations of multiple features. Here are a pair of snapshots that show the traffic along two road segments. Suppose city planners are using snapshots like these to study local traffic, and they hire you to design the data form that will be used to record the information from these snapshots. You'll have to record the time and date, the segment number, the direction of traffic, lane widths, the type of vehicle, speed, and the distance to the vehicle in front. What would your form look like? We've given this task to over 100 students ranging from middle school to university. Here's a small sample of the data forms that students have created. Many students use a narrative form rather than a table to encode the data. In this example, each bullet contains a single piece of information. So here the westbound width of the road is 15 feet. The back SUV is 50 feet behind. Also, the SUV is going 75 miles per hour. All the information is here, but in a form that is highly unorganized and unpredictable. By comparison, other narratives such as this one are highly structured, with related information written in specific locations and clustered under headings with snapshot-level information. In this form, the information is organized in a table with the 8 attributes listed along the top. Each row holds all the information about a single vehicle. So the first vehicle is an SUV going 75 miles per hour, heading west, 50 feet behind the vehicle in front, at 8 a.m. on segment 3 on this date and on a road that's 15 feet wide. This is the type of data table used by most statistical software programs, including Fathom and Tinkerplots. To structure data in this way, you have to be willing to consider the width of the road, for example, as a feature of a vehicle rather than a feature of a road. This is a rather odd way to think about it, and we believe this is why the participants in our study more often created nested tables similar to this one. In this form, information about the speed, type, and following distance of each vehicle is again organized as a row by column table, but these vehicle tables are nested within lanes that have a direction and a width. And here lanes are further nested within segments that have an ID number, a date, and a time. So in this structure, we can recognize 3 types of objects: vehicles, lanes, and segments. The various pieces of information are associated with the object they most naturally belong to. Another feature of the nested table is that it avoids repetitive encoding of values that are the same for many vehicles, such as date, direction, and time. Many students mention this as an advantage of the nested table over the flat table. Based on this research, we've come up with this tentative design of a data table in DG, which uses a nested structure. Students in our field tests seem to understand this kind of table and work with it rather intuitively. We're still analyzing data from the traffic problem, including about 25 individual interviews with middle and high school students, where they talk aloud as they created and filled in their data form. We're also testing out different designs in DG with students in the classroom. We expect to have a journal article ready for submission sometime in the fall.